that T of Z can be used to construct an infinite number of conserved currents. Any J of Z which is equal to epsilon of Z, chal raha hai Samaran? T of Z for any analytic function epsilon is a conserved current. Okay, and one convenient basis for such currents is the following. Let's say that epsilon of Z is equal to Z to the power n plus 1 an. Okay, so an's are just some numbers. We're focusing on one particular value of n. We just take Jn of Z to be Z to the power n plus 1 T of Z. This was a conserved current. Right? This is true for all values, all integer values of n. Okay. Now, what I'm going to do now is to derive the commutation relations of the charges that corresponding to these particular currents. Okay? Now, the manipulation that I'm going to do sounds strange if you think of it just on the plane, but it's very natural when you think of where the plane came from. So remember, the underlying theory lived in Lorentzian space on a cylinder. When what we did was to take time on that cylinder, analytically continue to Euclidean time, and then do a Weyl transformation that converted the cylinder to the plane. Okay? On the cylinder, where do charges naturally lie? Is on constant time slices. Okay? We look at a constant time slice, we do the analytic continuation to Euclidean space, remains a constant time slice of the cylinder, and then we do the Weyl transformation to the plane. That becomes a constant radial. So charges, okay, charges are naturally computed on constant radial slices. And as we derived last time, when we were trying to, you remember we worked out this Stokes theorem, when we looked at we looked at the question of how to take the Ward identity for currents and convert that into a local operator product statement. Okay? You remember we converted that Stokes theorem that we did del dot J and then converted it into a line integral. We worked it out in analytic and anti-analytic space, and we got del integral Jz del Z minus integral Jz bar del Z bar, dz bar. Okay? So, the current, the charge associated with this thing, okay, the charge associated with a particular current is naturally evaluated on a slice of constant radius, and in fact the nature of that charge is Jz dz minus Jz bar dz bar integrated. In our particular example, there's no Jz bar. Our current is completely holomorphic. We have only Z component of the current, and the Z component is holomorphic. That's why it was conserved. Okay, so up to some 2 pi's, which we will get straight to get the standard answer, our current here is simply Jz is equal to Z to the power n plus 1 T of Z. Okay, and so I'll call this, just following usual conventions, I'll call this guy Ln. So Ln is Z to the power n plus 1 Tz. Okay? Remember, Ln was the current associated with an infinitesimal coordinate transformation. Z goes to Z plus whatever appeared here. Okay? So it's Z to the power n plus 1. So for instance, if we want a scale transformation, so Z goes to Z plus alpha times Z. That would be scaling Z. That would be L0, because n would be 1 to make it linear. So Z to the power n plus 1, this coordinate change is associated with this particular quantity that we call Ln. L0 we see is a scale transformation. Okay, L minus 1 we see is just a translation. Because if we set n equals -1, there's no power of z here. So z is just shifted by something that's independent of z, which is what we call a translation. So L-1 is a translation, L0 is a scale transformation, and L1 is what will turn out to be a special conformal transformation. We will come back to that as we go along. Okay, right now this is just a name. Okay, so the charge corresponding to this, there was this current, and the charge corresponding to this current, Ln, is equal to integral dz. I think I'll put a 1 over 2 pi I. We'll see what normalization we need. Okay, dz, z to the pi n plus 1 t of z. Okay, this integrated along this contour, along the lines of the discussion in the previous class for an arbitrary current. Great. So this is a charge. Now, the question I want the answer to is, what is Ln times Lm? Commutator of Ln. This is equal to what? Okay. Why do I want to know the answer to this question? It was a very natural question to ask. Every time you have a symmetry in a quantum system, the set of all symmetries forms a Lie algebra, right? Because of associativity, it forms a Lie algebra. And what we're doing is to compute the commutation relations of that Lie algebra for this particular infinite symmetry that we have. Is this clear?
So you have expanded epsilon z and
epsilon of z is the most general analytic function, and in general it takes the form this over n. Now the coefficient of an I'm calling the nth current, its charge I'm calling Ln. Okay, so if I just make the transformation z to the pi n plus 1, nothing else, that current I'm associating with Ln. The charge for that is Ln.
Right.
Is this clear?
Yeah. So in 2 dimensions there is
infinite number of symmetries associated with each of these charges for every integer.
Right. So basically, what is the interpretation of other Ln's rather than -1, 0?
Well, all of them have this interpretation. You know, it's a particular. You remember we argued that every conformal coordinate transformation was a symmetry of our theory, because a conformal coordinate transformation changed the metric in a manner that could be undone by a Weyl transformation. And a Weyl transformation is precisely the invariance of a conformal field. So you could perform a coordinate change that changed the metric. That was a trivial thing. But then you could put the metric back to the original form by performing a Weyl transformation. That combined operation is a conformal transformation and is a symmetry of the theory. Now you remember the set of all conformal coordinate transformations were all analytic transformations of z, z as a function only of z. That's all of these. So these are the various conformal transformations. Okay? L0, L1 and L-1 will be special because they will be globally defined on a sphere. What? They will form a subalgebra, and they're a special subalgebra because they're a subalgebra whose vector fields are well defined globally on the sphere. What? On a sphere, yeah, S2. What's the difference between a Riemann sphere and a sphere? It's a sphere. Okay, mathematicians like to put fancy names. It's irritating. Okay, okay, it's what you imagine. It's a round thing. Okay, 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 excellent. Okay, so this is what will be special. That these will be the transformation will be everywhere well defined. Will nowhere go singular on a sphere. Okay, for all the other transformations, somewhere these coordinate changes will go singular on the sphere. They're still locally useful to derive word identities, but they will not be globally useful to derive constraints on correlation functions on the sphere, for instance. Okay, we will discuss this as we go. Right now, we're just looking at local consequences of symmetries. Okay, but excellent questions all. Keep it up. Okay, so the question we want to ask is, what is ln commutator ln? Okay, why we're asking this question is clear. Every time we've got a bunch of symmetries, we try to find the commutation relations because that characterizes the Lie algebra and therefore in the end the group. Okay, so it's clear we want to know the answer to this question. Now how do we ask the answer? How do we address this question? First, what does this mean? Okay, now let us remember, we're going to try to compute this commutator using path integrals. Because path integrals are often useful for manipulations. But commutator is something, it differs only because of ordering of operators. So it feels like a very Hilbert space thing. How does a path integral compute a commutator? Well, this is a very simple way if you want the commutator at equal times. Exactly. Path integrals always compute time-ordered correlation functions. So if we have two operators inserted at equal time, this is true just in quantum mechanics, O1 of t and O2 of t, I want to compute this commutator. I want O1, O2 minus O2, O1. Now, quantum mechanics is like Arabic, right? You read it that way. So earlier times go on the right, later times go on the left. Okay? So if I want O1, O2, what I will do, in general in quantum mechanics, if I want O1 t, O2 t minus O2 t, O1 t, I can think of it this way. This guy is the same as O1 of t plus epsilon in the limit epsilon goes to 0, O2t. And this guy is the same as O2 of t and O1 of t minus epsilon. And I take the limit epsilon goes to 0. But now, once I've written it this way, these operators are automatically time ordered. So this is the same as time ordered. O1 t plus epsilon O2 t minus O2 t O1 t minus epsilon. And time ordered insertions are what path integrals compute. So if we're just computing path integral, we drop the time order. Just compute the path integral of O1 at t plus epsilon, O2, minus O2 at t, O1 at t minus epsilon. And that will automatically give us the time ordered order. And then in the limit epsilon goes to 0, will give us the commutator. Is this clear? Okay. Now, we said this all for time order. Time ordering was on the cylinder. When we translate to the plane, that becomes radial order. Okay? So later times are larger radius. Earlier times are smaller radius. Okay. So suppose I want to compute.
In path integral,
Yes.
We can compute the correlation function.
Yes.
So whatever we can compute is the correlation function of commutator of 1 and 2.
Yes.
So basically in operator format, then I have to reduce then.
Yes, but you see, you can compute this correlation function with arbitrary insertions of other operators.
Okay.
If you get some relationship for correlation functions without saying what other operator insertions are, you've got an operator relation.
Okay.
Because it means that relation holds no matter what else you put.
Okay. It's just like an integration with some f and something. Then
It's like that. Or even more an even nearer analogy is, if every matrix element of an operator equation holds, then the operator equation holds.
okay. Okay.
If IMJ is equal to INJ, where M and N are two matrices, then M is equal to N.
Right.
If it's true for all I and all J.
Right.
So it's like that.
It's like,
Is this clear? Okay? Okay. Excellent. So what we want to do, we said, was to compute LM, LN. Okay? And we're going to do this using this trick. So what do we have to compute? First, we do the following. We want to, let's say we want to do it at unit time, unit radius. Okay? Okay, now it would have helped if there was colored chalk. It doesn't matter. I'm sure there's some secret stash somewhere, but okay. let's do the following. Let's say that this guy was z to the power n plus 1 t of z dz. And then this was at t equals 1, so really at unit radius. And then I put this guy like this. This is z to the power m plus 1 t of z. And both of these are integrated. So let me call one of them z and the other one w. Let's call this z and this w. Okay? Both of these are integrated. This is integrated over z on the contour. This is integrated over w. Minus, once again, I'm not touching the n. So this guy is z to the power, we call it w, w to the power n plus 1 t of w. But now this time I put this guy here, z to the power m plus 1 t of z. Both of these are along the contours as indicated by the arrows. This is the contour integral we want to compute, and we could have operators inserted here, doesn't matter. Okay, but we're assuming that there are no operators inserted at time 1. So where these contours are going, it's not hitting any other operators. Okay, because that would change things. Fine. Now, I have to perform 2 contour integrals. So let me first keep the omega contour for later. So I choose some point on the, this was z and this was omega. Right? So I choose some point on omega and I imagine performing the z contour. So then what am I doing? So I've chosen some point on omega, so this is now a dotted line, this is the unit radius, some omega point, I'm not changing it. And I compute this contour minus same point in omega and this contour. Okay. Now, what can we say? Let's fix omega, let's fix w. And I'm doing a contour integral over z. So I want to know the analytic properties of the integrand as a function of z. Everywhere that the integrand is analytic, I can move the contours without penalty because of Cauchy's theorem. However, if there's a place where the integrand is not analytic in z, I cannot move the contour through that point without penalty. Now, what do we know about t of z? We know that t of z is an analytic function except at locations of other insertions. This we derived by using Noether's theorem last time. Do you remember? Ward identities. It's followed from the fact that del dot j was equal to 0 everywhere except at the locations of other insertions. So t of z is an analytic function but could have some non-analyticities at locations of other insertions. Okay, we're assuming that there are no other insertions in this little band where all the manipulations are happening, other than, of course, t of w. T of z can have non-analyticities at the location of t of w, and in fact does. That's what we computed at the beginning of I reminded you of at the beginning of this class. The operator product expansion between t of z and w. There are non-analyticities at z equals w. So we cannot move this Cauchy integral through this point, but we can move it freely everywhere else. Okay, so now let's do that. So what I'll do is I'll take this integrand and put it on the unit axis with a bump. Now I've changed the contour, so this is really at z equals 1. Is this clear? I've paid no penalty for this because of Cauchy's theorem. I do the same thing here. This is also on the unit axis, except that the bump has to be now down because I cannot move through this point. Is this clear? Now, I take the difference between these two. Since this contour and this contour are the same, and in the same direction, those paths cancel each other. Okay? So that the difference here, can you see, is this minus this, but minus the same as flipping direction. So it's this. Okay? So you see that the z integral can be performed merely by looking at the integral of this integrand around w. But by Cauchy's theorem, that only picks out the pole in the integrand around w. So all we have to do is to find the pole in the integrand around w. Is this clear? Okay. Now, this is of course a very easy thing to do. Let's do it. The most difficult thing in this calculation is keeping track of which is m and which is n. Okay, so we have z to the power m plus 1 t of z, omega to the power n plus 1 t of w. That was the integrand. Okay. We want to find the pole in this. The pole comes from a non-analyticity at z equals w. Notice that all our manipulations are in a band. They don't touch the origin. So everything we are saying is correct whether m is positive or negative. The fact that there's another non-analyticity at 0, if n is a large negative number and m is a large, doesn't bother us at all. Okay? So our now what we want to find is non-analyticities at z equals w. But we know how to do that because that was the whole point of the operator product expansion. Okay, so we get z to the power m plus 1, w to the power n plus 1, and then we had c by z by 12, z minus w to the power 4 plus 2t of w, z minus w, the whole thing squared, plus del t of w by z minus w. Everything else is regular, so will not contribute. So these are the only terms that can contribute. So we've got this object, and we want to find the pole at z equals w. Right? Okay. So now what we want to do is to take this object and Taylor expand it around w. Okay? The Taylor expansion can be of the Taylor expansion of third order will hit this and produce a pole. A first order will hit this and produce a pole. And a zeroth order will hit this and produce a pole. Is this clear? Okay. So let's do that Taylor expansion. Okay. Let's first take the term that's at zeroth order. The term at zeroth order is just replace z by w. So w to the power m plus n plus 2 del t of w by z minus w integral over w. Now, because I put the 1 over 2 pi i's in my integrand, okay, so let's say that my integrand had 1 over 2 pi I, the whole thing square. What? Integration over w, z, now let me remember which was z. Z was the outer guy, right? So I've done the integral over z. I've picked out the pole. What remains is the integral over w. Is this clear? Let me draw the diagram again. I had a fixed w point and I was doing the integral over z. That is the pole in z minus w. But, you know, that was at one point z, at one point w, I'm going to do this manipulation at every w. Remember, the original integrand had an integration over w. That's the integral I've written here. Is this clear? Okay? And what? Z minus omega shouldn't be. Thank you. Thank you. Thank you. Thank you. Thank you. That was the confusion. Sorry. There was this. Is this clear? And I chose my integrand to have a factor of 1 over 2 pi I. So that Cauchy's theorem kills 1 over 2 pi I. I have one of them left. Is this clear? Okay, so this is term 1. Now what about term 2? Term 2 requires us to Taylor expand this guy to first order. So when we Taylor expand to first order, we get a factor of m plus 1 times w to the power m plus n plus 1. Now there's a factor of 2 because there was a 2 there. T of w dw, always 1 over 2 pi I. Okay, and then there is also the Taylor expansion around m plus to third order. Okay. Okay. So Taylor expansion to third order, well, the third order derivative is m plus 1 into m minus 1 by 6. And then we have a z minus w, the whole thing, cube. We knock those guys out. And so we will get c by, it's a large number. C by 12. Was that really C by 12? It's a large number.
I think the factor is in the numerator.
Factor of 6 is in the numerator. I see. Sorry, maybe I'm doing something terribly stupid, but I've got f of x is equal to sum over n fn of 0 by n factorial x to the power n. So if I want the term that is of order x to the power n, shouldn't I just compute the nth derivative? It was c by 2, not 12? Thank you. That makes a lot of sense. Thank you. This is c by 2. Yeah. C by, okay, thank you. Thank you. C by 2 makes a lot of sense. Okay, so now where were we? We have c by 12 now here. Okay. Times, now integral omega to the power, well, m plus n minus 1 t of omega d omega. Okay, what I need to do is to add these guys up. Okay, now all of these two are already something nice. This guy is a bit irritating because it has a dead t of omega 1 beta. Thank you. A number. Thank you. 1. Thank you. So bottom is just some number which we'll calculate in a minute. Middle guy is some charge. The upper guy is a bit irritating because it's got del t, but we know how to deal with that. We integrate by parts. Okay, so this guy is the same as minus m plus n plus 2, okay, by 2 pi I integral omega to the power m plus n plus 1 t of omega d omega. So it's a term of the same form as this guy. We can club them together. 2 and minus 2 cancel. 2m and this becomes m minus n. So we see that the final answer is m minus n integral z to the power m plus n plus 1 omega. T of omega d omega, always with the 1 over 2 pi I, plus 1 over 2 pi I C into m plus 1 into m minus 1 integral omega to the power m plus 1 n minus 1 d omega. Okay, now what remains is to do these integrals. Okay, to do the integral, well, this integral is very easy to do because it's 0 unless m plus n is equal to 0, and then it cancels the 1 over 2 pi I to give us 1. So we get that this guy, this is equal to delta m plus n 0 into C into m plus 1 into m minus 1. What? M minus 1. What? By 12. Huh? And what about this guy? Well, by definition, this guy with the 2 pi I is L of m plus n. And so we conclude that Ln is equal to Ln is equal to L of m plus n plus C into m plus 1 into m minus 1 by 12 delta m plus n 0. Delta m minus n. Thank you. M minus n. Yes. M minus n. Okay. And this boxed equation has a name. It's called the Virasoro algebra. Okay. Our derivation of this Virasoro algebra, as you see, was extremely simple. All it used was operator product expansions and Cauchy's theorem. Okay? And a lot of conformal field theory. You know, a lot of conformal field theory is complex analysis, operator product expansions, and sometimes using unitarity. These three things together give you a lot of things in conformal field theory. Okay. Now, you can ask yourself, what does this algebra mean? Those of you who, were keeping track of what we were doing, remember that what we started with was a sort of coordinate transformation. Okay? That Lm was associated with the coordinate transformation. Delta z is equal to z to the power m plus 1 del z. Okay? And so you might ask, well, if all we're doing is coordinate transformations, what's the big deal in computing commutation relations of coordinate transformations? I know how to do that. Because coordinate transformations are, delta z was z. Coordinate transformations are generated by vector fields. Okay? And the Lie bracket of these vector fields gives us the commutator of two coordinate transformations. So what is the vector field associated with this? It's simply z to the power m plus 1 del z. So let's try the classical computation. Let's try this times z to the power n plus 1 del z. And see how well it compares with what we had up there. Okay? Well, that's an easy calculation because you see, when we do this, we can have this guy hitting this guy, which will give us n plus 1 n plus 1 z to the power m plus n plus 1 del z. Or we could have this guy hitting this guy, which will give us with a minus sign, minus m plus 1 z to the power m plus n plus 1 del z. Okay. So now there is some minus sign issue here, which you will forgive me for. It's probably one of these. Okay, I'll write down what I'm getting. I'm getting, if we put an I or it's probably one of these inside versus outside things.
No.
It's probably one of these things where, you know, if you do something inside, the order changes. Do you know what I mean? If you change x to f of x, and then change that f to some g of y, you're getting different things from doing it from outside. It's probably one of these. So you forgive me this minus sign, which we could track down if you want, but up to this minus sign, we are getting n. I'm just getting what we want. Minus m L z bar m plus n plus 1 del z. We could track down this minus sign if you were very worried about it. Maybe there's some I missed, I'm not sure. Okay? But let's not focus on that. What's important is that once we get that minus sign straight, this is the same as this. What this classical calculation does not give is this quantity. Okay. So now you might be a little puzzled by this. How can it be that we have an algebra which had some commutation relations? So algebra was algebra of coordinate, conformal coordinate transformations. How can it be that quantum mechanics does not implement, changes the algebra? Well, the way it's working, there are two things. I mean, first, it does, but there are two ways to try to make peace with this. The first is this, you see, and this is really the important point. Remember that the quantum symmetry was not simply that of coordinate transformations. It was coordinate transformations coupled with a Weyl transformation. Okay? So, roughly speaking, and we will make this more precise as we go along, in fact, maybe even today in today's lecture, this part was the contribution from the coordinate changes. This part knows about the Weyl transformations. Okay? Weyl as we will see as we go along, what's happening is that the Weyl transformations are doing something a little funny. It's not completely a symmetry. It's a bit confusing, but this is how it goes. There's another way to say this that people sometimes like. And I think these are somehow equivalent. The other way that people sometimes like is the following thing. Classically, if you've got a Lie algebra, it's implemented on, some vector space. It's implemented by some commutation rules. Now suppose you've got a physical algebra. Suppose you've got a physical algebra in a physical system, and you want to implement it on your Hilbert space. Now you have to remember the following fact. You have to remember that states in quantum mechanics are not themselves physical. It's only states modulo rescalings that are physical. A state psi and a state alpha times psi, where alpha is an arbitrary complex number, is exactly the same state. Now, if you want the state to be normalized, the norm of alpha has to be set to 1, but the phase of alpha is completely arbitrary. So two states that differ by a phase are completely the same state. Every quantity that you obtain from these two states is the same. If you want matrix elements between two different states, then relative phases are physical, but overall phase change of states is unphysical. Makes no difference at all. So you see, quantum mechanics has the option of implementing symmetries a little more broadly than classical mechanics does. Instead of implementing it in the sense that two things that should be the same must be the same in Hilbert space. It has the option of implementing it so that two things that must be the same can lead you to the same state up to a phase. Okay? Mathematicians have studied the extra freedom this buys you. Okay? And in simple situations, and the phases have to obey some consistency conditions for this whole thing to make sense. And solving for these consistency conditions gives us what people sometimes call the maximal central extension of the Lie algebra that you're interested in. Okay? So having the commutation relations obeyed up to phase on states is equivalent to changing the commutation relations in a certain way, and that change is by a relatively tame kind of factor. Okay? So this, you can also think of this central charge term here as coming from this kind of central extension. Okay? Coming from the fact that this diffeomorphism algebra is not being implemented faithfully, but only up to these phases. People sometimes use the word projective representation for this. Okay? These are more or less the same thing. The second way will not prove useful for us to think about. The first way will be useful because we will constantly worry about how things change under Weyl transformations. I will make the first statement more precise in equations as we go along. Okay. Questions or comments about this Virasoro algebra?
Is that why it's multiplied by a delta function when m plus n is 0?
Yeah, it's why it's multiplied by unit operator. You see, it's not multiplied by an operator, just by identity. Identity is the phase. Just acting on the state, changing it by itself.
And it changes only when m plus n is 0.
Yes, that had to be because the charges had to cancel, right?
Yeah, it doesn't keep the scalings and the conformal translation.
Yes. The comment here is that if m is 0, 1 or minus 1, this number is 0. Because the product of three things which are 0 when m is equal to 0, 1 and minus 1. So this quantity disappears if you look at the algebra generated by L0, L1 and L minus 1. And that in fact is a subalgebra.
But couldn't we add a central charge term for the subalgebra?
Well, you've seen what we got, right? We started with the OP. It's the only thing it could be. And we got what we got. Yes, so this is all that there is. Yeah. You're asking why not? Okay. You see, there's some mathematical understanding of this. But let me tell you what. For finite Lie groups, there is a general result. Suppose you've got a finite Lie group, and then you ask for the most general projective representation of that group. The most general projective representation is the representation of what is called the covering group. It's a faithful representation of what's called the covering group. So for instance, the most general projective representation of SO3 is a faithful representation of SU2. Okay? I don't know what the result is for SL2R, but I suspect that you just cannot do it. Yeah, but there are, see, there's this co-cycle condition for these phases, and it's a stringent condition. You cannot do whatever you want with it. Okay.
So we see that in case of, for m equals to minus 1, 0 and 1,
Yes.
the C would not appear, and
It does not appear in this
these
commission.
two things exactly matches. So, and you commented about this appearance of C is like some other quantum mysteries or something. So,
But it's not completely a mystery. We'll unravel it. But, okay, yeah.
but and as we know that these three are global, so can we, mix up these two concepts like?
Is the fact that they are global related? Probably in some sense. There may be something, that's a good question, I don't know the answer. There may be, it sounds tempting to say that there is a relation, right? I don't know I don't know the reason for that. I'll think about that. If I find anything to say, I'll tell you. It's a good question. Okay, excellent. As we go along in our studies, you see, C was a completely undetermined quantity. So some of you may be tempted to wonder, could C just be 0? In that case, if C is 0, we get the same classical algebra. Indeed, we want C equals 0 in string theory. The world sheet of the string has to have C equals 0. However, for more general applications, there is an obstruction to having C equals 0. As we will show as we go along, any unitary theory has to have positive values of C, minimum value being half. So if we want a unitary theory, C cannot be 0. World sheet of the string gets away with this by allowing for non-unitarity at intermediate stages. The C ghosts, BC ghosts are not unitary.
So can you please repeat this statement? I mean.
Okay. Okay. We will see within a class or two that in any unitary theory, C has to be greater than 0. It cannot be 0. 0 violates unitarity. In fact, as we go along, we will see that C has to be greater than half. Unitarity puts a bound on C. Okay? So if you're interested in studying unitary theories, C cannot be 0. Now, when we study string theory, we are often interested in the world sheet of the string. In that case, we really demand C is equal to 0. Because we want our string theory to be really while invariant. And we achieve that by allowing for non-unitarity at the level of the world sheet. The miracle of string theory is that non-unitarity at the level of world sheet is consistent with unitarity in spacetime. The no-ghost theorem of string theory. This is a miracle. Okay? But if you were not interested in string theory, if the space-time theory you were interested in, you were studying a system which you knew had to be unitary, it was 1 plus 1 dimensional conformally invariant, then C cannot be 0. Okay? So for that purpose, C equals 0 is not a very interesting theory. Okay? So we have to learn to make peace with C not 0. Okay? We will try to do that perhaps, a bit of that perhaps even in this class. Okay, any other questions or comments before we continue? Okay, excellent. So we have studied the Virasoro algebra. Let's continue on this board. Now, the next thing I wanted to do was to tell you about primary operators and tell you about the operator product expansion between the stress tensor and primary operators. So, what is a primary operator? In general, in a while invariant theory, doesn't have to be 2 dimensions. A primary operator is an operator that transforms as follows. You know, a while invariant theory is a theory that has the same correlation functions on the manifold with metric G and manifold with metric G times e to the power 2 phi. So suppose I choose manifold with metric G mu nu and I put insertions of some O's at some locations. Okay, if I get the same correlation functions by choosing G mu nu times e to the power 2 phi and putting insertions of e to the power delta phi. I may have to change this to minus in a minute. Okay. If you see, when I say something is while invariant, it means that there is a dictionary such that on manifold with metric G and manifold with metric G times e to the power 2 phi, there is some change I can do for my insertion so that I get the same answers. I'm suggesting that if there are operators for which this change works, I may have to put a minus in a minute, we'll see in a minute. But then I will call these operators primary operators of dimension delta. Okay? So let's see. Now, we talked about this in the first class, but I'll just work this out again in a moment. Imagine that O is a scalar operator. And all correlation functions of O have to match. But suppose this is true, then we can relate delta to the dimension of the operator as follows. On any manifold, O of x, O of y, in a conformally invariant theory, Weyl invariant theory, has a 2-point function x minus y mu, x minus y nu, g mu nu to the power 2 delta, to the power delta. Right? So if this dictionary is going to be the same for an operator of okay, let's call this delta, let's call this a delta prime. We'll choose the convention there so that delta prime is delta. If this is going to be the same, then it should be true that e to the power delta prime phi at let's do the particular case of a rescaling to start with. So just phi is constant. So e to the power delta prime phi, e to the power delta prime phi by x minus y e to the power e to the power 2 phi g x minus y mu nu to the power delta has to be independent of phi. Okay, and that works if delta is equal to delta prime. Okay, so if we've got a Weyl invariant theory such that the operator transforms in this manner, then that operator in normal language is an operator of weight delta. Is an operator of weight delta in the conformal field theory sense. Okay? So primary operators have weight delta in conformal field theory. The reverse is not necessarily true. It's not true that every operator that has weight delta is a primary operator that transforms this way. Primaries are more special. We will understand this as we go on. What I want to do is to understand how primary operators of weight delta transform under conformal transformations. Okay? And so now that we've done this check, I'm rubbing it out. This was just a check that I had got the minus sign correct. Okay? So we have that g mu nu O is the same as e to the power 2 phi g mu nu e to the power delta phi O. What this means is I've got a bunch of O's, all its correlation functions, on the manifold with metric G, the same as all the correlation functions of this on the manifold with metric this. Right, this is what it means. Now, suppose we call the coordinates in this space. Suppose we call the coordinates in this space. Now I specialize to 2 dimensions. We call the coordinates in this space Z prime. Okay? So far I have not done any change of coordinates here. So the coordinates in this space are also Z prime. But suppose phi takes the form that so that e to the power 2 phi is equal to del z by del f of z prime by del z prime, del f bar of z prime by del z bar prime. Suppose e to the power 2 phi happens to be of this form, meaning happens to be of the form that can be undone by a conformal coordinate transformation. Okay. Then on this space here, I make the change of coordinates. Okay. So in this space, I make the change of coordinates. So I go to a new coordinate z is equal to f of z prime. Z bar is equal to f bar of z bar prime. Okay? And what do I get? I get that in this space, okay, now I just have, I have insertions at the points z and z bar. So let me say it more clearly. What I wanted to say was that G mu nu, so this now becomes what? Once I do this coordinate change, in terms of z, the metric, in terms of z, the metric goes back to G mu nu. Right? Because we have the metric being dz by dz, del z by del z prime, del z bar by del z bar prime, dz prime, dz bar prime. And then this is the same as dz bar. We undid the conformal transformation, the Weyl transformation. Right? So now, I have a third thing that is equal. The third thing is that the metric is G mu nu, okay? And O is now a function of Z. But Z and Z prime are related by the fact that Z is that given function of Z prime. Okay? So we have Z, which is Z, which I'll continue to call f of Z prime, f bar of Z prime, and that scaling is still there. So we have e to the power delta phi. Now, as we will see in conformal field theories, delta will be the sum of a holomorphic weight and an anti-holomorphic weight, h plus h bar. Okay, maybe we've already talked about this. You see, there's complex rescalings. A linear rescaling is scaling. I mean, a real rescaling is scaling, and a phase rescaling was angular momentum. And the linear combination of real rescaling and phase rescaling this way is h, and real rescaling and phase rescaling that way is h bar. Anyway, we'll talk about it in more detail. But just, okay, so this goes like h plus h bar phi. Now, this e to the power phi I'm getting a factor of 2 off, just a minute. H plus h bar, just a minute. H is equal to okay, forget this h and h bar. Let me just do it with delta. We'll come back to h. So this delta I think is correct. So we've got this delta phi. I'm going to write this as delta by 2 times 2. So e to the power 2 phi was del f by del z, del f by del z bar. And then we have this to the power delta by 2, delta by 2. Is this clear? So what was the conclusion from this exercise? The conclusion from this exercise was that right. The conclusion for this of this exercise was that if you have correlation functions in metric G mu nu and O of Z prime, that is the same as the correlation functions in metric G mu nu and O of f of Z prime, f bar of Z bar prime, times del f by del z to the power delta by 2, del f bar by del z to the power delta by 2. Now presumably delta, for a scalar operator, delta by 2 is h. Just a minute. Just a minute. Yeah, where did I get my 2 wrong? Just a minute. I've got a 2 factor wrong. I've got a 2 factor wrong. Where did I mess up on this? Maybe there. Maybe here I messed up here. G mu nu to the power delta why 2 delta? It's a square there. Sorry, I've messed up in some stupid place. Just a minute. What? Give me 1 minute. If somebody knows the answer, that will help a lot. But just, that's what I'm wondering. Suppose I take the stress tensor. Okay, let's check. Suppose I take the stress tensor T. T has H equals 2. We know that T has J equals 2 and it has dimension 2. Okay, and therefore H is equal to delta plus J by 2. It's correct. It's correct. So let's I'll have to tell you about the relationship between H and delta. But there is a delta by 2 there. So let's take the stress tensor as an example. Stress tensor has angular momentum 2 because it has two lower indices. It has dimension 2 because it's a stress tensor in 2 dimensions. So delta is 2, J is equal to 2, and our conventions always gives it H equals 2. So H is delta plus J by 2. When J is 0, H is just delta by 2. Yeah. Okay, great. So this is fine. When we've got operators with spin, okay, I'm just going to write this as H and H bar. When we've got operators with spin, what I've not taken into account here is that I've assumed that O is a scalar. When we've got operators with indices, so with spin, there's additional transformations under the diffeomorphism. Okay, and so this will just turn into H and H bar. So for a scalar operator, we've just checked that that's correct because H and H bar are both delta by 2. But when you do it more carefully, including the spin, it will always be correct. So H this way and H bar that way. Okay, I'll leave that as an exercise for you. What? H is the thing we call conformal. It's the thing we call conformal spin. Exactly. Okay. So now focus on the final result. The final result is that for a primary operator, O of Z prime is the same, has the same correlation functions as O of f of Z prime, f bar of Z bar prime, del f by del Z prime to the power h del f bar by del z bar prime to the power h bar.
So the correlation function of any operator is non-zero spin.
Yes?
The spin will not arrive, only delta arrive.
What?
Suppose O has some spin,
Yes.
then but in its own self correlation function.
Yeah. Yes?
Only conformal weight arrives, but not in.
What do you mean arrives?
I mean, this is something distance to the power 2 delta.
Oh, we would have to do that calculation differently. The distance to the power 2 delta is only for scalar operators.
Only for scalar operators.
Yes, because that quantity transforms like a spin zero quantity, right? The more general answer will be, the more general answer is 1 over z minus z prime, the whole thing to the power 2h, 1 over z bar minus z bar prime to the power 2h bar. That will be the more general answer. Okay, and that will be consistent with everything we've done. Okay, this is our final answer, and I want to make sure you understand what it means. Here in this answer, there is no metric, because the metric is the same on both sides. In intermediate steps, we changed the metric, but we undid that. So the insertion of an operator O, okay, if I insert operators O, and then I change all operators in the insertion, according to this rule, let's say they're only primary operators, I will get the same answers for all correlation functions. This is what that statement means. Is this clear? Is this clear? So if we have these operators which transform under Weyl transformations in this very special way, then they transform under conformal transformations in this way. What do I mean by transform under conformal transformations this way? I need a rule so that correlation functions will be the same. This is the rule. Is this clear? Okay. So now,
This is the definition of primary operator.
it came from the fact that primary operators had very simple transformations under Weyl transformations. This you can treat as a definition, but this is where it comes from. It comes from the fact that there were operators that had good scaling transformation properties under Weyl transformations. Okay? Then now people who do conformal field theory sort of axiomatically say this is my definition. But physics-wise, why was this the right definition? For the reason we've just described. Okay? Yes? Where does it come from? Okay. You see, operators like this always transform just with delta phi under O under Weyl transformations. But now there was a second job. There was a second step in the operation, which is we did a diffeomorphism. Under a diffeomorphism, a scalar operator remains unchanged. But an operator with some spin transforms the index. So let's suppose that we had an operator which had 2z, let's say 1z component, 2z components, let's say. Okay, then how would the transformation have gone in the second step? In the step from the Weyl frame to undoing the metric. Okay, this index would have to transform according to the coordinate change. So we would pick up two extra factors of del z by del z prime to the power 2. That's what would change the HNX. Is this clear? What you will get some number of del z by del z to some power and some del z bar by del z bar to some power. Whatever that power is, for the del z by this we call that h. Whatever it is for the del f we call h bar. Okay, and this will just turn into delta plus whatever, delta plus j by 2 and delta by j minus 2. Okay. Okay, so that's where it comes from. I'm not doing the algebra. I'm not working it out, but you understand, right? Okay, excellent. Fine. Now that we've got this rule for primary operators, let's see what this rule becomes for under infinitesimal conformal transformations. Okay, so suppose f of z prime was equal to z prime plus epsilon of z prime, where epsilon was infinitesimal. Okay, what does this right hand side become? Well, and then there's a similar thing for the f bar, I'm not writing it. Well, there are two terms. One we get by Taylor expanding. That is epsilon del z o. That's one term. And the second term is plus h del epsilon by del z times o. That clear? Because it's infinitesimal. Okay? So under an infinitesimal conformal transformation, this is the transformation of a primary operator. Okay? Now, let us understand what this means for the operator product expansion between the stress tensor and a primary operator. Okay? We know that the current for the infinitesimal conformal transformation generated by epsilon is simply epsilon of z Tz. So it must be that if I take this OP, it must be that the residue of the pole is this. Residue of the pole at 0 is this. Because you remember that the residue of the pole at 0 governs the transformation of an operator under the symmetry generated by a current. This is the thing we studied last time. This you remember. Is this clear? So it must be that the OP is such that the residue of the pole is 0. This term simply has an epsilon. So clearly there must be in this thing del z O at 0 by z. Because then the residue will give you this term. This term is del epsilon by del z. How will this come about? It's like what we had in the Virasoro algebra. It comes about if there is a double pole and you have to expand the numerator in Taylor expansion. Okay? So, so this will come out if we have an h of 0 by z square. If you want, I can put this at w so that. Do you see that if we have this, then if I multiply this by epsilon of z, okay, if I multiply this by epsilon of z, then I Taylor expand once, I will get this term, and this without any Taylor expansion will give me this term. Is this clear? So that infinitesimal transformation translates into this operator product expansion. Is this clear? I hope I'm not going too fast. Is this clear? So if we have a primary operator, of dimension, holomorphic dimension h, whatever, conformal, whatever it was called, dimension h, then its operator product expansion with the stress tensor has to take this form. As we explained last time, this part was totally obvious. It just tells you that under a translation, O translates like derivative. Okay? This part is more interesting. It tells you that under a scaling, it has dimension h. What's really key is that there were no earlier terms. There were no other more singular terms. That's what makes this operator. Okay? The H term is the statement that it's got holomorphic dimension H. Del ZO is the statement that under translations it. That is okay. All that is reasonable. What's interesting is that there were no other singularities. This was the most singular term. Okay? Okay. T is not a primary operator. Excellent. Excellent. In fact, that tells you that T does not transform under Weyl transformations, like e to the power 2 times phi. And in fact, is the thing that, in fact, maybe if we have the time now, maybe we can try to use that to figure out how T transforms under Weyl transformations. Okay, but let's focus on this for a minute. Okay, is this clear? Now, recall that not all operators are primary operators. A primary operator was something that transformed homogeneously under Weyl transformations. So suppose I have O goes to e to the power 2, whatever, delta phi. Now I take derivative of O. Suppose I look at del mu. I know how O transforms under Weyl transformations. Therefore, I know how its derivative transforms. So one term will be when I take the derivative on O and I pull out this e to the power delta phi out. So that term will transform with weight delta, whatever, under this transformation. But the second term will be when I take this derivative and hit the phi, will give you a non-homogeneous transformation property, not just something that depends just on phi, but also on derivatives of phi. Okay? So it's a general result that almost always there will be exceptions to this rule, and they will be very interesting. These will be null states. Okay? But generically, if an operator is a primary operator, its derivatives are not primary operators. Okay? So, in higher dimensional conformal field theories, in fact, this is what a primary operator is. You know, once I give you an operator, I can make many more operators by acting with derivatives on this. Those are what we call descendants. And in higher dimensional conformal field theories, the only way of making descendants is by acting with derivatives. So, the space of all operators are this. There's this nice operator and all its derivatives. Those are its descendants. All the operators that you cannot write as derivatives of something else are primary in higher dimensional conformal field theories. In two-dimensional conformal field theories, there are more ways of being descendants, because you've got this infinite dimensional symmetry algebra. Okay? At least to start with for now. But one thing that is certainly clear is that if you have a primary, it is generically not true that its descendants are that its derivatives are primaries. Okay, so great. Now let us quickly go through this little derivation, or maybe that's for next time. Will we finish it? Okay. Let me tell you in words what we're going to do, and I'll do the algebra next time. I'll indicate how it goes. Maybe some of you can fill out the algebra. Maybe one of you can present it to us next time. Okay. Let me indicate what. The first question we're going to ask is the question you asked. How does the stress tensor transform under Weyl transformations? Okay, so we had this TT stress tensor, which is T of Z, T of 0, was C by 2 Z to the 4 plus 2T of 0 Z square plus del T by Z. Okay, had this term been absent, It would have been an example of this. Okay? It would have transformed, it would then have been an operator that transformed under Weil transformations, like e to the power 2 times delta. Okay? But there is this additional term. What does it mean? Well, let's try to figure this out. So suppose I act with an epsilon of z. Okay? Suppose I act with an epsilon of z, t of z on t0. And I look at the change, this kind of conformal transformation. What change does it do on t0? Okay? In order to get the change, I've got the paths that we already understand. I'm going to ignore them. It's the new term that I'm interested in. The new term is going to be the third derivative of this guy, epsilon z by 12 c epsilon q, third derivative by 12, and that's it. That's the change. The delta t is equal to this. What? Derivative at 0. Thank you. Derivative at 0, correct. Okay. Now, what does this mean? What does this mean? You see, if I perform this is going to be the result of an anomalous transformation, non-primary type transformation under Weil transforms. So I should identify the effective Weil factor that was involved in this transformation. How do I do that? I just go through the chain of logic we outlined last class, in the last 10 minutes. We had correlation functions, then we Weil transformed, then we diffeomorphismed to go back to the same metric. Okay? And I identify what was the Weil transformation in that step. Well, the Weil transformation was del f by del epsilon to the power h. Well, del f by del z to the power h. That was the Weil transformation. Okay? There's an infinitesimal Weil transformation here. You have to get the numbers right, but that will be proportional to del epsilon by del z. Because del f by del z, and there'll be a factor of 2, but I'm not writing all that. So it will be, the Weil transformation will be epsilon prime of z. Proportional to this. Is this clear? So let's write epsilon prime of z. You have to get the factors right. This is your exercise for next class. Okay, let's call that delta of phi. Phi is the Weil transformation. So what we're seeing is that up to some factors, which I'm not writing, there's certainly a c, but I'm not writing the numbers, we get del z squared times delta phi. So we're seeing that the stress tensor transforms under a Weil transformation apart from the homogeneous transformation by an additional term which is del z squared times the change, infinitesimal change in the Weil factor around flat space. Now, you see, this is interesting already, but it has a dramatic consequence. The consequence that it has is that it cannot be that the stress tensor is traceless in this theorem. Why is that? You see, the Weil transformation factor has to be generally covariant, has to obey diffeomorphism invariance. So it has to be part of a rule that transforms like a tensor. So delta t mim is what? We've already seen that delta t zz is equal to del z squared times delta phi. That's pretty good. There's an obvious covariantization of this. The obvious covariantization of this is delta t mu nu is equal to del mu phi. With numbers I'm not writing. That's your exercise. Okay? However, there's a problem with this transformation. See, stress tensors are always conserved. And if I compute this, it is generally not conserved. It's right hand side, del mu t mu nu is not 0. Can I fix this up? Well, suppose I take del nu minus g mu nu del squared of phi. This term would not show up for tzz because g has gz z bar as the only non-zero quantity. But now if I take del dot of this, get del squared here, that cancels. Okay? So basically this is the only tensorial completion of the statement that we've computed. Tensorial completion that is consistent with general principles including conservation of the stress tensor. Exactly. Exactly. And this tells you that z bar cannot completely be 0. Okay? But it allows you to compute what z bar has to be. Because now we've also found the Weil transformation property of z bar. Okay? So Weil transformation up to some number is del squared phi for z bar clearly. For z bar we take trace. Okay? This trace will give us a factor of 1, this trace will give us a factor of 2. They won't cancel each other, there will be something left over. And z bar will be proportional to del square phi. So now z bar can't be 0. But what could it be? It's 0 on flat space. This we've been very careful to ensure. But now we've moved away from flat space. Everything here has no operator on the right hand side, it's just 1. So all it can depend on is geometry. Is there a nice geometrical invariant quantity that at leading order in phi becomes del square phi? There's the Ricci scale. Okay? And so this analysis forces us to conclude, when we do it properly, that T, the trace of the stress tensor, is in fact C by 12. All the factors so far have been nonsense, but this is correct. R. Okay? I'll go through this analysis in the next class quantitatively, because it's very important. Okay? But if one of you were to work it out, that would be great. Okay? This C, therefore, is sometimes called the Weil anomaly, because it tells you that any theory with non-zero C is not quite Weil invariant. Okay? But the Weil anomaly is a very tame object because the anomaly is independent of all operators. Okay? And in fact, by integrating the Weil anomaly, we get an equation that tells us, let's say I'm computing a partition function. The partition function of the theory on some metric is not exactly the same as the partition function of the theory on a Weil rescale metric, but is related to it by a factor that we can determine in terms of the C. We'll determine that next class. Okay? So it's almost a Weil invariant theory. Not quite Weil invariant, but Weil covariant, in the sense that we know how the theory transforms under Weil transformations. Is this clear? Okay? So this little extra term has a dramatic consequence. It tells you, as Omkar explained to us, that the theory is not quite Weil invariant. The stress tensor is not quite 0 when viewed on a curved manifold. But that's life. However, we will be able to determine, you give me correlation, you want correlation functions of Weil transform metric, I will tell you the answer. Will not be quite invariant, but almost. Okay? Fine. Let's stop the class here today. And next class we'll continue with this. The plan, I was thinking through the plan for this class. My plan is, hopefully by next class we will complete this general analysis of the kinematical structure of conformal field theories. Then I thought we could spend maybe 3 classes describing free conformal theories. we could talk about free bosons with periodicity, free fermions, and Bose-Fermi duality, bosonization. 3 or 4 classes about that. I mean, there's an enormous amount to learn just about these free theories. And then, after that, we would go on to studying minimal models. At least that is my hope. I hope we can maintain the space. Yes?
So in this, this while anomaly is coming just for stress tensor.
But stress?
Why not for primary operators also?
Why not for primary operators? Yeah, good question. Good question. Good question. You see, the stress tensor is special because it tells you, even when you have no operators in the theory, it tells you how the partition function of the theory transforms. Right? So suppose I was interested in, you give me the partition function of the theory on some metric G. I want to know the partition function of some metric, some other metric. All 2-dimensional metrics can be related to each other by diffeomorphisms and Weyl transformations up to some small finite additional pieces of data. Okay? So the stress tensor, of course, is an operator in the theory, but its Weyl transformation is telling you much more than about a particular operator. It's telling you that even without operator insertions, the partition function of the theory is not how it's invariant, the extent to which it's invariant or not under Weyl transformations. That's what it's telling you about. Okay? Now, why not operators? Could happen that some operators that you classically thought would be Weyl invariant will not be. An example of such an operator will be just the X field for a free boson. Okay, it looks like a perfectly good classical object, but quantum mechanically its correlation functions will be sort of singular. But why not? Why not? Why not? Let's see, what does this? You're asking, could it have been that the you see, the thing is this. We will see this in more detail as we go on. But let's imagine the following. We have all these L operators. Okay. Okay. In order to properly address your question, please hang on for 5 more minutes. We'll say one thing. Okay, it's a good question, and let us see the implications of this operator. You're asking about, okay, so let us see the implications of this OPE expansion of T with O in terms of the Virasoro algebra. Okay, that will help me answer the question. Okay, so let me do 3 minutes of algebra. Remember, we have T of Z, O of 0 goes like H O of 0 by Z squared plus del O by Z. Okay, now let me now compute the following. Let me now compute Lm O of 0. or the action, more O of 0 I'm thinking of as a state, because it's an operator inserted at the state. So let me compute Lm acting on O. Is what this means clear? It's the state generated by the operator insertion at 0. Okay. So in order to compute that, what I have is integral z to the power m plus 1 t of z O of 0 or O of 0 dz. Okay. Now, if we have the operator product expansion of the form that we've described above, okay, we can compute this. Okay, we can compute this. You see, what we will get is the Taylor expansion of the first term, so we'll get m plus 1 z to the power m z to the power m and t of z sorry. So this is now, so I should replace this. So I replace this by h O of 0 by z squared, so z to the power m plus 1 plus integral of z to the power m plus 1 del O by z. Okay. Yeah, so this is very simple. Here I just cancel one of the z's. I have m, and so I get something non-zero when m is 0, that's from here. So I get L0 on O is equal to HO. That's the first statement. And I get L minus 1. L minus 1 on O is equal to del O. Okay. Now, if we had higher order singularities in this expansion, okay, if we had higher order singularities in this expansion, then can you see I would have got L positives on that quantity being something non-zero. Now, L positives carry negative energy. L positives reduce the energy of a state, whereas L negatives increase the energy of the state. That you can see from the commutation relation between L0 and Lm. Okay, L0 is the energy, the holomorphic energy. And so the LMs carry energy, which is L from the commutation relation we had for the Virasoro algebra. You can see this. Okay, so if you have states with higher singularities, then L's with negative energy give you something non-zero on it. Okay. Now, suppose that happens. We get on whatever we get, we act with all the negative energy objects. We have two options. Either this thing will keep going, or it will terminate. Okay? If it terminates, then every positive L, every negative energy L, every L with positive, with 1 and higher, annihilates the state by definition, because if it didn't, then it would give you another state with lower energy. Okay? All such states that are annihilated by all positive LMs, have the OP of a primary operator. So in a theory where you have a lowest energy states within your module, where your representations of the Virasoro algebra are of the lowest energy sort, the bottom of that tower is always a primary operator.
So you are saying that primary operators carry the least energy.
That's right. That's right. Least energy for all the states that you can get by acting on that with stress tensors. Okay? So that the representation theory, again we will study all of this in more detail, but the representation theory of this Virasoro algebra has a lowest energy state and then states you can build on that, which are higher and higher energy by acting with the L minus M's. If there was no primary operator, I think what you're asking is suppose there were no primary operators. I've not said anything about the form of the primary operators. But your question was suppose there didn't exist primary operators, or there were things with other commutation relations, other OPs. There would be no lowest energy states. Okay? So that is possible, but in theories that are so weird we probably don't want to study them. Okay? So primary operators from another point of view are the lowest energy states within a representation module. And representation theory allows representations with lowest energy states, that goes all the way. But it allows representations with these things, and these are the ones that are of physical relevance.
So stress tensors are not lowest energies?
Not lowest energies. In fact, stress tensors are descendants of the identity operator. But the identity operator is the lowest energy state. Okay, because descendants are anything that you can make by acting with LMs on this guy, in this module. LMs are, some resummation of T. So T acting on identity is the stress tensor. So it's a descendant of identity.
And identity is a prime?
Is a primary. It's the best possible primary. Is this clear? Okay, great question. Other questions? Okay, excellent. Let's continue next time.